test. No pressure. We don't count the score. Okay, so you are supposed to do it badly, and you should be able to do it well after the entire course. So don't worry if you have no idea what the test is about. Okay? You don't need to cheat to make a high score. Try to answer in any way you like. For Taiwanese, if you need translation on any words, I can help you. If you need to write it in Chinese, it's okay. So there's 20 minutes for the pre-test. No pressure, no worries. Please do not have discussion. Okay. Okay. This is just for the project. So no worries if you have no idea what's going on. Try to answer in any way you want. You only have 20 minutes. Does anyone need a pen? Okay. He needs a pen. If you know nothing about the exam, it's okay. By the way, there are some typo over here. Number 9, 14, and 15. There are some typo over here. Do you need a pen? You need a pen? Anyone need a pen? Sure. No issues. Anything is fine. Don't use your blood. The score doesn't count, no worries. The score doesn't count. Do as much as you can. no pressure. The score doesn't count. Okay, this is pre-test. No pressure. Just do as much as you can. The score doesn't count. No pressure. There are actually some easy questions, like choose A, B, C, or D, right? So if you have no idea, at least make some guess. Right? I think number 3 is pretty easy, A or B. 50% of changes. So it's impossible for you to get 0 points. Because question 14 and 15, you can make your own number. So in this sheet, it's impossible you get empty result. You at least can say something somewhere. Yeah, this is a pretest. No pressure, just for, the score doesn't count.
Okay, thank you
So
very much.
just do as much as you can.
Okay, thank you.
Okay? Test doesn't count, the score doesn't count. No pressure, don't worry. Have fun. Oh, does any Taiwanese need translation of any word? You can. Number 8, okay. Von Mises is a person's name. 一个人的名字. So, if you don't know, you don't know. Any, yeah. Number 6, fatigue. 疲劳. Fatigue is 疲劳. Any other words you need? Number 7, okay. Endurance limit. 耐久极限. Anything else? Okay, any Other language? Translation in any other language? Yeah.
Pulleys.
12. A pulley. 皮带的. Yeah. Belt is 皮带. Pulley is 皮带的. Oh, by the way, does any non-Taiwanese need me to tell more about a word? Maybe you don't even know the word. What is a pulley? Anyone need help? You can let me know. Don't be shy. It's okay. final minute. Okay, so Tom, can you help to collect? Now we collect all the sheets. Does anyone want to drop the books? Okay. Ah. Okay, which one are you more curious about? Which question? Anyone? Who really wants to know the answer right now? Tell me, yeah. AMR, autonomous mobile robot. Autonomous means a robot system can do something by its own will. Yes, it has its own intelligence. Mobile means it moves. Robot. Robot is like a robot. Has an arm, has a sensor, making decisions. Robot, 机器人, right? So autonomous mobile robot. Did I mention AMR? Because remember in our syllabus, I turned it off already. In the syllabus, in one of the week, we are going to talk about the project. And in the project, we basically work on designs for AMR, okay? So if you were here yesterday, or if you remember what I said yesterday, actually, the answer was given to you yesterday. Okay, so AMR is right here. See, I will be introducing AMR at the middle of the semester, but I told you what was AMR yesterday. Okay, anyway, no worries. Any other question you are interested? No? Yeah, they are quite boring, right? This course is supposed to be quite boring because mechanical design has a lot of design concept. I think the design concept is important. But in order to implement those concepts, you need some math and physics. Math and physics could be quite boring. Okay, but for myself, I love math and physics. I hope you do the same. So in question number 1, what is safety factor of a mechanical design? So basically, what does it mean? If I'm a person, I have a strength of 100 unit, whatever unit, pressure or stress unit, and someone hit me with a punch with some kind of strength in the scale of 10 units. So my body is 10 times stronger than the punch. I will be okay. So 10 times. My safety factor is 10. Now if someone hit me with a rate of 90 units, now my strength is 100, the force is like 90. Then it's very close. I could have danger because the strength of the punch is reaching to the limit of my strength.
Okay, so safety factor is a ratio of strength and stress. They are actually in the same unit. They need to be described in the same unit, usually in the unit of pressure or in the unit of stress. Stress and pressure has the same unit. So safety factor has no dimension. It's a ratio. Okay? You need to get back to the course material you took in the past about mechanics of materials. You need to get familiar with those again, because in this course, they show up a lot. Okay? So what does this box mean? This box means a very tiny element everywhere in an object, in the object that you are investigating. So if you are studying the strength of this table, you took a tiny bit, a small box, and you have a super microscope and try to observe what's happening surrounding the box. And if you have some kind of a Superman eyes, you can visualize, okay, there's some stress over there, here and there. And when you took the small box, you took it in a very tiny square and you assign some kind of coordinate x, y, and z, and you put the box next to the coordinate. So whatever force that is toward the direction of x, you will describe it as x. Okay, and there's another, but from here you can tell there are two indices underneath sigma. So what are those two representing? So the first one represents the location. So from here on this particular one, it's the surface YZ, like facing x direction. So the first index are, all of them are x. So it's indicating the force or the stress is located on this surface. And the second index is representing its direction. Okay, so XX represents stress on this surface pointing toward x direction. Okay, likewise, it should be quite easy to understand. So for the ones that is normal to the surface, they are called the normal stresses. And for the ones that lies on those surfaces, they are called the shear stresses. So this should be quite easy, I hope, quite easy for you. So now we review elasticity. So when a material carries a load, it deforms a little bit. When you release the force, it returns back to its original shape. No permanent deformation or permanent damage. That means that force was within some kind of elastic region of its material property. So in this course, we mostly talk about elastic force. So, which means all the deformations are within the elastic region. Can someone tell me why? Why don't we talk about some stress that is outside of the elastic region? Why don't we talk about somewhere here? Can someone figure out why? Think about some mechanical part in your car or bicycle. Would you design something that could be facing a serious load in this region? That means your bicycle will fail. When you ride a bicycle and then some part just collapse or breaks. As a designer, we design mechanical parts that can carry the load. So we are not supposed to build something that cannot carry a load. So the designer of this table make certain assumption where someone could be doing this and it won't fail. Very good. Okay, but if someone try to do some extreme action with it and really try to break it, those are like extreme situations. No designer can cover all kinds of situations. So most of the time, designer design a part based on the most common situations. So the designer assume even you have a car accident, you don't jump off the hill and then crash into ocean, right? So no designer can design a car that can save you if you try to just fall from 10th floor high, right? Nobody can save you. But if you are just having a regular car accident, accidentally bump into the wall, the design should be strong enough so the parts saves you. It carries the load. It doesn't release the load on you. If the load releases on your body, then you die, right? Okay, anyway, there's some key information right here. In the elastic region, that means the relationship between the stress and strain is linear. So they are having this linear relationship with a coefficient. E is the Young's modulus. Usually larger means a stronger material. Smaller means a weaker material. And there's a point right here, somewhere right here, where the stress and strain is about to have nonlinear relation. So if you increase the amount of stress applied to the material, then you will have nonlinear deformation greater than usual. So the material cannot handle this kind of load above yield strength. So the word yield means, okay, I'm about to greatly deform and I cannot recover back to my own shape unless you are, what's the English of Haizewang? One Piece. One Piece character. What is his name? What? Luffy. Unless you're Luffy, right? You have very strong elasticity. You don't yield, right? But anyway, what is ultimate tensile strength? It's like the largest tensile force that you can carry, and by doing a tensile test, you realize this material can never reach some state that has higher strength. Okay, so sometimes you also need to be aware of this as well. So, same example, if I'm designing a car and I'm having a car crash, if the part cannot carry some extreme load, you know when you bump into the wall, the part will crash, but at least carry some load by making deformations. But if the amount of load the material can carry is way lower than the load that applies to the body, the car, then it's dangerous. It's like you're driving a car made of wood or paper. You don't want to drive a paper car, right? You want to drive a car that is made of steel, made of metal. Okay, so this ultimate tensile strength is still important in mechanical design. Later on in the future, you will see sometimes we still put this in a design equation. We worry about this. We worry about how strong the material is. Okay. So by definition, the stress can be computed by the load over area. By definition, the strain can be computed by the deformation over its original length. Okay, so with those we can, and also by this linear equation, we can put everything together and get this equation. And then we can rewrite this equation into this final one. What does it mean? The amount of deformation equals to, or you can say this is related to 4 important factors. How much load that is applied to the material, what's its original size or length, E, Young's modulus, the material property. A is like the geometry. If you design, for example, you apply a load to this particular cylinder, if this cylinder is thicker, it will be stronger, right? So the cross-section area matters. So geometry matters. Actually, in one of the questions, it's telling you what are important. Geometry affects the cross-section area. The material you choose, are you choosing a stronger one or a weaker one? What else did I say? How much load? Greater loads give you greater deformation, right? And there's something else, how safe you are looking for. Not in this slide. How safe you're looking for is some design parameter right here. Okay, so this page and the following page are two different concepts, but they are very related. Okay, now we talk about, we will be talking about two kinds of ways to apply load to a part. One is bending, the other one is twisting. Okay, what's the difference? Bending and twisting, basically they are like applying loads, generating moment, and cause some kind of rotation of the material. And depends on how you describe the coordinate system. So for like a long object like this, if you apply force from both sides and then you are carrying at the middle, it bends, right? It bends. So it's generating bending moment. And if you try to squeeze it like this, the load you apply to the long object is following a different coordinate. This time you are not bending this way, you are like twisting. So the moment you generated is having a different direction. So we first talk about bending moment. Over here you can see, if you apply the force right here from top to bottom, and if there's a support, there's a distance from the support to where you apply the load. So if you multiply how much load you apply and multiply the load and the distance, you get how much moment you apply to this object, right? So you have a bending moment like this. On the opposite side, there will be reacting bending moment, so they have a balance of moments, okay? So when you have a situation like this, if you make a cut inside, what will happen? Actually, inside the material, there's stress. And you can tell the stress inside the material won't be the same at every position. We care about the stress everywhere, in fact. We need to know the stress everywhere inside the material. But at the end, once we know the stress distribution or the stress everywhere, at the end, we just need to focus on one point. The position with the largest stress. Because the position with the largest stress will break or will fail first. So if somewhere is having lower stress, we don't care. That position doesn't fail. So in this particular case, everywhere at the upper edge or the lower edge are having the largest stress. So if I try to bend this long object, I know the first position it could be breaking will be somewhere on the top, on this top line, or somewhere at the bottom. Nothing at the middle will break earlier than the top or the bottom. So when we make mechanical design, we only need to focus on the position with the largest stress. As long as we apply enough safety factor to that position, and that position won't break based on how much safety I provide to the system. If that worst position doesn't break, any other places won't break. Okay, so the most important concept of mechanical design is to find where is the exact position that is the weakest, or where is the position that could be breaking the first. So like the example I did on this table, if I sit in a weird way, it generates some kind of uneven distribution of my heavy load on the table. Somewhere in the table will break. Okay, maybe one of the part right here or somewhere over there, you don't know. Because today I sit in this way, the other day I sit in this way, right? So as a mechanical designer, I need to make a lot of analysis. Okay, how about I apply force like in this way, apply force in this way, and then I start to find, okay, in some situation when I do this, some of the mechanical part is carrying so much load. For example, maybe over here it's carrying so much load. I need to change the geometry so the load can be evenly distributed. So when you see a circular part right here, definitely it's not because of how good it looks. This circular shape allows the geometry to distribute the stress better than a 90-degree corner. Because if you have a sharp corner, a straight corner, usually it has very large stress. And if I do this, that straight 90-degree corner will break. So not only the circular shape looks nice, but also it has a good advantage of distributing loads. Okay? So now you understand. When you make a mechanical design, you need to know where has the worst case, where has the maximum stress. So in the following several weeks, we will be finding which position has the largest load, or which position has the maximum stress. We will focus on that particular point or area, and we will make proper design so that at that worst position, it won't fail. And how do we decide whether it's failing or not? As long as we have enough safety factor. As long as the strength of that particular position is stronger than your stress, then you should be safe. Okay? That's the idea. Let me see what time it is. Okay. Now, since we're trying to compute how much stress you have inside the material, then you need some math. And here's something you need to get back to your previous lecture notes and get familiar with those. I'm not sure if I can finish this in 10 minutes. Maybe I quickly go over this, but I need you to go back and have some reading about this. So, Y represent a position where you are making your investigation. So Y describes the current position. And we believe the stress inside this area is having a linear relationship with its position. We believe at the center, we call the neutral axis, there's no stress. So when we bend in this way, we believe on the upper part is having a tensile stress. Basically, it's like someone is pulling from the right, pulling you. Tensile is like a pulling. And at the bottom, it's like it's pushing. So it's like a compression, the stress in compression. So we believe, since this is a linear material, linear forced behavior, we believe if this is zero, the neutral point has zero stress, so supposedly it should be linearly growing as you move your starting point from the neutral toward the edge. That's why we have a model. Maybe it's k times the distance, okay? But we don't know how much. Now, in order to compute how much stress are applied inside the material, we can use the knowledge we know from the condition. We already know we apply certain moment from the edge, and we know when we make a cut, there's some stress generating at the like a middle of the material. And no matter where you cut the material, supposedly that particular material is following a balance of moment. So you can just make a random cut and then compute how much moment these stress will be contributing, and they should be balancing with the moment you apply. That's the trick of what we're doing right here. So all the moment contributed by the stress everywhere will be balanced out by the stress you apply here. This is the stress you apply here. This is how you compute all the moment generated everywhere right here on the right-hand side. So if you focus on this particular stress at this tiny area, we made a small cut right here with a very tiny height. D means a very small increment of y. So we just focus on this small area. Right here, there are some force toward right pulling the material. And if you have force, if you have the stress multiplying the sorry, you should use your stress right here, multiplying the area. So basically this is the area. Then you will have the total force that is applied on this small area, the pink area. So if you use the force going the same way, multiplying the distance, that's a calculation of moment, right? So stress times area, that's force. Force times the distance, that's the moment going clockwise. Now, why do we take an integral? Integral is like a summation. So if you sum the moment that you generated everywhere, that's taking an integral. And what's changing when you make the sum everywhere is y. So y goes from negative c, this is c, to positive c. This is why y goes from negative c to positive c. Once you are able to sum all the moment generated everywhere, that is balanced out by the moment you generated on the left-hand side, you have that equation. So the following will be just math. Okay, so we assume the stress is k times y, so just plug it in. So k times, so you have a ky squared over here. You can rewrite the first equation and ends up with something like this. K is a constant. So k can be taken out of the integral, and you can tell, okay, k equals to m over some integral right there. And we realize this is basically area moment of inertia. So if the shape of this geometry changes, the area moment of inertia changes. So what does it mean? If I can borrow a book, can someone have anyone has a book? No book. No one has a book. Oh, yes, maybe my book, okay. So, same book. If I try to bend the book, if
I bend this way, it could be easily bended. Because when I bend it in the same way, I'm studying along this direction and I try to compute so-called area moment of inertia. It's not so strong. Okay, so I could easily generate stress along this direction. How about the other way, here? I still can bend the book quite easily. Because along this way, if I compute area moment of inertia, this material is not too strong to fight against my bending moment. However, if I try to bend in this way, can you see me bend this book? If I apply this force and this force, and I want to twist, not twist, try to deform the book and form a weird shape, like a bend. If I want to, bend the book in this way, if I can do it, I don't need to be here, right? It's so difficult, but same book, same strength. But if I bend it in this way and this way, so easy, but in this way, so hard, right? Or in this way, this is almost impossible. Because along those directions, the area moment of inertia shows stronger ability to fight against bending. So area moment of inertia is some quantity that fights against bending. Okay? So go back, try to read those. Where to find this PowerPoint? It's online. On the course webpage, if you check on this PPT, that should be the exact same one. Review of solid mechanics. Exact same PPT, I think. Yes. So it's up there. Today's video will be up really soon. So if you like what I said, you like some of the jokes that I made today, you can watch today's video. Or if you want to check some other old jokes in the past, then check other videos in the past. If you like Chinese, I do have Chinese versions. If you have difficulty understanding, in the past I taught this course in Chinese. So for Taiwanese, this is a good way for you to have better learning. Okay, that's it. That's everything. See you next week. I know someone wants to add the course, Jiaxuan. Okay, please come to here.